Okay, fossils. Conventionally, these are the remains of an organism's body fossils, or their tracks and trails, which are called trace fossils. And these vary enormously in composition, preservation, and information content. A big problem in very old rocks is identifying fossils based on appearance alone. After all, we are trained to see pattern even if there is none. And in really old things, there might all just be microbial remains. This is why you want supporting lines of evidence to identify materials as evidence of past life. Now, body fossils are the remains of an organism's body, okay? Things like its skeleton, like this skull here, or impressions of the skin, impressions of leaves, isolated teeth, for example, like these shark's teeth here, or isolated feathers. Trace fossils, on the other hand, are preserved tracks, trails, borings, root traces, or other marks made by an organism while it was alive. An example is this footprint of a sheep-like animal that you can see here, where just the impression of the animal walking over a muddy surface. Now, there are also chemical fossils. These include biomarkers, organic chemicals that are distinctive of a particular type of organism. They are usually not the original molecule. Instead, biomarkers usually reflect the loss of labile components, such as double bonds, hydrogen, and OH radicals that are attached to carbon chains. Labile components are things that organisms like to eat. Often, only the carbon chains are preserved. An example is the chemical phytol, a major side chain off of chlorophyll A, which is used in photosynthesis. It is converted to phytane by the loss of OH radicals and double bonds. Phytane is preserved in oil because bacteria are not very interested in the carbon chain that forms the backbone of the phytane. There's just not enough energy to be had to eat this stuff. Another example is the production of steranes from steroids. These include the steroid cholesterol, as is typical of eukaryotes. So if you find steranes made from cholesterol in sediments, then we know that eukaryotes must have been around. Another type of chemical fossil is ancient DNA. This is pretty new. I didn't talk about this maybe 15 years ago when I started teaching this class. The field started by extracting DNA out of frozen bones, and that worked because freezing preserves DNA pretty well. Now, more recently, the field is increasingly using the technique of whole genome methods, where we use computers to match up short fragments of DNA to reconstruct the whole DNA strand. This method is well suited to DNA that is not perfectly preserved, where all we have are relatively short strands of genetic material. Another type of fossil is the history of life written in an organism's living genes, namely its modern DNA. We can use the DNA of living organisms to figure out when the major groups of organisms first evolved. This method is using the concept of what we call molecular clocks, which we will get to later in the class. Finally, there's the environmental context in which we find fossil remains. We can look to modern environments to see what kinds of organisms and modes of life we expect, say, to live on a beach or in a mudflat. Oftentimes, the type of microbial life in those environments are similar because the microbes have experienced the same selective pressures over time. An example is the discovery of glass-eating microbes in volcanic pillow basalts from 3.48 billion-year-old lavas in South Africa that closely resemble those found in modern pillow lavas. Another example is the discovery of very similar microbial assemblages in modern tidal flats and those from 800-million-year-old Spitsbergen localities up in the North Atlantic, described by Andy Knoll in his book, Life on a Young Planet. The key is that in very old rocks, we should look to modern analogs for those environments. If we find them, we can have more confidence that we've correctly identified simple structures, like little cellular structures, as evidence of life.